Very nice to be here in Princeton and at IAS. I wanted to start with this observational image. This is, I wanted to describe, provide an explanation. The goal of this talk would be to provide a sort of physical explanation for the X-ray activity versus rotation behavior that's been observed for some time. This trend of, this is the this is the X-ray luminosity of low-mass stars divided by their bolometric luminosity. And this is the rotation period divided by a convection timescale. This trend, and I'll come back to this plot a bit further, has defied explanation, in particular the way that this saturates at, for fast rotators. And this, so I'll come back to this, and that's sort of the ultimate goal. To get to the explanation, or at least a plausible explanation, I need to take you on a kind of tour through what activity is. And I'll begin a bit with the sun. So the sun is, this is X-ray image of the sun through cycle period. So over 11-year period, the sun wanes in X-rays and then revamps in X-rays. This is, these images are active regions which represent essentially the outcome of magnetic loops that pop up on the surface of the sun and dissipate. And the cycle period is, this trend is 11 years for going from the quiescent to active. The solar luminosity, in this case, the X-ray luminosity varies by a little bit more than a factor of 10 in that respect. It's also, this activity is also seen, of course, in H alpha, and it's measured coincident with sunspots. So this is a sunspot history. As the sunspots increase, the activity is correspondingly increased. The representation of that by magnetic fields popping through the surface and is a consistent with that trend. So the spots and the activity regions pop up at the equator, and then, pop up at mid-latitudes and then migrate towards the equator. So this trend of mid-latitude popping up of magnetic structures migrating towards the equator is part of the activity cycle. So, and it's the spots that appear, there are trends with, we know that they're magnetic also because we measure the sign of the magnetic field. And each cycle, the leading spots and the average mean field reverses. So the spots come up with the leading spot having one polarity during one cycle, and then during the next cycle, the polarity switches, and the overall average field also switches sign as a function of cycle. So these are all, and also overall, the solar magnetic field is kind of a combination of open and closed field lines. Open field lines along which the fast solar wind moves, really more large-scale fields, and then at the equator, the fields are closed, and there's more active regions at the equator. The X-ray luminosity is brighter, more because the loops that pop up are closed, and then as they open up to become the large-scale field, which then actually drifts towards the poles, you see the X-ray luminosity only when there's dissipation. So when there's no dissipation, you don't see a bright luminosity. So that overall pattern of activity is consistent with both X-rays. I'll give you some other signatures as well. X-ray brightening, sunspots, and magnetic polarity all correlate over the active and decorrelate. They all correlate in strength over the active phases of the sun. So it's clearly a magnetic activity. And then by extension, one would think that this is also true in other stars. Just a few other features here. So this is a sunspot during an active, so sort of during an active part of the cycle. In the non-active part of the cycle, one also sees lots of small-scale magnetic structure. The small-scale magnetic structure is kind of persistent throughout the active and the non-active parts of the cycle. And as I say, they only differ by factors a little bit more than an order of magnitude in total X-ray luminosity. So even when the sun is quiescent, it's still an X-ray emitter. The X-ray luminosity of the sun is some million times less than its bolometric luminosity. Now, more specifically, the enterprise of studying activity encompasses lots of different subfields. If you look at a particular active site, flare, and you blow it up, one can observe now with something like 500 kilometer resolution on the surface. You can extract the magnetic structure, and these are sites of magnetic reconnection. So these flares have been well modeled by an X point here, magnetic reconnection that accelerates particles downward, heats up a loop that brightens, and the properties of this magnetic reconnection process are in fact studied. I mention this to sort of emphasize that the study of reconnection in solar flares, the particle acceleration, the structure, the evolution of a single solar flare is really an entire subfield of plasma astrophysics. People spend a lot of time looking at the individual, trying to understand the various processes. That includes the particle spectrum. So this is just a time evolution of the structure in UV, and here's sites of X-ray emission, and a lot of effort trying to understand how the X-rays are produced, what produces their spectrum. These are collisionless plasma acceleration processes often, and mapping the structure of these, the temperature evolution, or fitting the spectra with a power law, or in this case it's a thermal flare, which is another issue. Some of these flares are highly non-thermal, some are thermal. That's an enterprise in and of itself. And approximately 50% of the flaring is overall, not per flare, but overall is kind of non-thermal. 50% ends up being thermal. So not entirely. So there is the morphological. There is so I mean, one can try to do detailed simulations of the process and see whether you get proper heating out, whether you get the structure of the magnetic field that pulls in. So no, and also you can also measure you can also in some cases measure the field in the region for its sign, and then so all of those things, when you put them all together, gives a picture. Then also there's the question of how fast the process is occurring, which has been a long-standing question. But then laboratory studies, for example, have now in here. In fact, I have that comment on the next. Is the team at the MRX has done laboratory studies of magnetic reconnection to look at the rate of how fast magnetic energy can dissipate. You need it to dissipate at a certain rate. That's been a long-standing problem. Under what conditions can magnetic fields dissipate with the seemingly observed configurations that they have? That's now, there's been a lot of progress in that, and it depends on the collisionality of the plasma and the non-collisionality of the plasma. So you can measure the density and the temperature, know the collisionality of the plasma, see whether the processes are consistent with the expectation from theory and from the laboratory. So there's a lot of evidence for that. One thing that's maybe not as, so this inverse Y picture has emerged kind of as the paradigm that works fairly well for these, but when you look more closely, you see there's lots of substructure in these things. So while the overall structure is consistent with kind of this overall reconnect, when you look more closely, there does seem to be lots of substructure at higher resolution. And so the basic picture that seems all consistent, that there is reconnection going on, and also you see the field evolution, simulations, all kinds of things. What's not so clear is how the particles are accelerated, what determines when they become thermal, what determines when they don't become thermal. Reconnection is really an environment for multiple acceleration mechanisms, and the relative dominance of any one of these is not quite understood. So that's kind of an active area of research. The particle, they're all active research, but the frontier, I think, is understanding how a given dissipation region produces a given particle spectrum. The solar reconnection events also has a flat, so if you integrate, so number as a function of energy is e to the minus 2. So that means if you integrate E dE, it's logarithmic in terms of number versus energy. So it's a very, so both large and small scale of the structure seem to be important for the overall heating. Now, so an individual reconnection process is its own physical laboratory and process, trying to understand the physics therein. But if you take a step back and you can ask now about more general questions about activity in stars and how they compare with that of the sun, and that becomes amenable to more simple modeling in a certain sense, as you'll see. So the focus here is on these low mass stars. So the sample, the graph of activities that I'll show really focus on samples that sample from F, G, K, and M. And part of the reason below a certain, for late enough stars, there's ionization questions, and so the physics of the ionization starts to enter how the field is coupled and such. But in this range, samples have been measured. There's going to be 800 stars that from which most of the information about the saturation of X-ray and dependence on bolometric luminosity and period is derived. So one point about these stars is that greater than 1/2 of a sun, the convection zone is interior, of course, and below it's fully convective. So in this range, so these below an M3.5 star, basically the star is fully convective. So there's a transition in the population of stars that I'll be considering here. But each of these has dynamo action, or at least convective action, that is near the surface, and so that's an important point. So the activity in low mass stars is measured by a number of signatures in different wave bands, and all of them are consistent with magnetic activity as well as in the sun. So there are only a few stars you actually measure the field reversals on. There's about 20, I know, but you do measure activity cycles in hundreds of stars. There's the Mount Wilson HK observatory. This chromospheric emission, calcium HK, is actually an emission feature at the core of an absorption line that you measure increases with activity and correlates with magnetic fields where you can measure them. So there's surface fields, chromospheric emission. All of these measurements of activity, which are also seen in the sun, correlate with the activities seen in, or the presumed activity seen in low mass stars. So it's thought that the X-ray activity and all of the these other signatures are all correlated with magnetic activity. And it's a consistent picture that's emerged. The cycle periods that you observe in other stars are greater than 7 years and less than 30 years, which are partly the upper limit, partly determined by the limit of data from the history of observing those stars. But what I want to now focus on more is the X-ray luminosity. If you think of this as a diagnostic of overall activity, it's one quantity, the overall X-ray luminosity. And in that sense, when you look at stars from a population, you're really drawing from an ensemble average of stars over at a random position in any cycle period they might have. So if you, for example, if you're plotting the luminosity of a population of stars and then making a overall curve, each star that you're picking from that sample is at some random position in its cycle period. And so effectively any trend that you want to predict is an ensemble average over many stars and over random positions in any of the cycle periods. So that's actually a kind of simplifying theoretical concept, as you'll also see. Yeah, so the width is I mean, that's a very reasonable explanation for the width, that you're not going to get a straight line, even because if you're in random period of cycles, each of the stars may have a different even though its rotation rate is not modulating on any time scale. So this is now coming back to that picture, just to note that there's a couple papers recently. So this one is, and these are the dependencies. So this 2 pi r0 is the Rossby number, and it's the rotation period divided by the convection time scale. And the best trends exhibited basically Lx over L bolometric with Rossby number. This is with period. There's some there's some ongoing debate between the fitting between these two papers, which I don't necessarily want to get into because both of them still look pretty good with respect to this. It has to do with basically the power law at below a low of this quantity of about 0.1, you can see that there's a tendency for flattening in the X-ray. So it's called the saturation in the X-ray to bolometric luminosity. And at high, at slow rotators, which is in this case long period, there's a clear dependence on rotation period. And it's best when it's normalized by the convection time scale. Yeah.
Is the convection time scale at the top of the convection zone, the bottom, at the average?
So it's typically some kind of average. I'll come to that in a moment, and that's going to be an important point. That's not that convection zone is that convection time scale is actually a theoretically determined.
When they shot the shots, what do they use?
They use a theoretically determined one. I'll come back to explain how that's and that's actually very important. Just and before getting into that detail, I just want to point out that the activities, understanding the activities, has some broader relevance. One of them is stellar aging. If younger stars are faster rotating, and you can correlate that with their age, then you have a way of aging stars, particularly field stars, which don't have associations with other. If you find stars in a collection, you know that the group. You can use HR diagram techniques, but if you're in the field, then you don't have that. Also, there's broader issues of understanding the influence of the X-ray emission on habitability zones, because they can knock out the atmosphere and you can lose water, hydrogen. And so these are other broader questions about activity in stars. And of course the subfields, all the subfields of the physics that goes on in understanding the actual production of the X-rays. And at very, very high resolution or high precision study of activity, it has this kind of, there's details about climate and space weather that are important. But also there's some of the physics of stars and has some analogs in accretion disks. And dynamos are of course going to be important because it's the generation of magnetic field, and not only that, but it's the large-scale magnetic field that is correlated with the X-ray activity as well. In other words, the sign of the field is very coherent and changing as the activity is changing. So just to so dynamos and X-ray activity, and to give you now, and I'm going to get a little bit into the dynamo theory to show how that makes the connection with this X-ray activity, and that's where some of the more details come in here. And I just want to classify dynamos. Dynamos are used in the literature in different ways. Often dynamo really just means amplification of magnetic energy exponentially. And there's really two fundamental classes when the field is on small scales. If you drive the system with some kind of flow, if the magnetic energy is at or below the scale you drive at, it's called a small scale dynamo. If the magnetic field can grow larger than the scale of the turbulence that you're driving at significantly, that's usually a large scale dynamo. And these are the classic dynamos for the sun that usually people think of when it's a dynamo, a large scale field. And that's the one that is focus on here. So to show the connection between the fields and how you start to get X-ray activity, let's look at the dynamo. And to give the big picture here, what I'm going to point out is that, so dynamo theory is complicated, but there are some missing ingredients that one can include even in simple models that have direct bearing on explaining this X-ray rotation curve. And that's the sort of how I want to take the rest of this talk to get to that point. So the basic thing with the sun, the reason why there's any connection at all between fields and the X-rays, of course, is that in cycle periods is something like this. So the rough picture, you have start with a field, and this is evolution through a cycle. It gets sheared by differential rotation somehow, and that winds up the field. Then you need to go to get the exponential amplification. The reason you need a dynamo, reason you need exponential amplification is that there's turbulent diffusion, which would otherwise just decay the field. In addition, the reversal periods of the sun are 11 years. The resistive diffusion time is like 10 to the 10 years. So you need something that happens on timescales which is macroscopic, associated with the macroscopic flows. But you also need it to sustain against the catastrophic diffusion of those macroscopic flows. So that combination is why you actually need a dynamo. And also we know the fact that the flux reverses in the sun is proof that dynamos operate in nature, because you couldn't just have evected the field from the proto thing. The flux would not change its sign. So that's this is the thing. So you take the flux of one sign, you wind it up. To get from the toroidal to part of the exponential process is that you need to get from this a poloidal field, so a toroidal field into a poloidal field, and then feed back into the toroidal field, and that's the feedback that you need. And there are various ways of getting that poloidal field from this toroidal field. One is just turbulent helical motions. As eddies rise up in a density gradient, they twist to conserve angular momentum, and that twist and rise is correlated in each hemisphere with a different sign. So and so you get these twists. Then when you add the fields together, you get a poloidal field and a toroidal field. And now your poloidal field, the average poloidal field, is now a mean field, and it can diffuse through and become your new, it produces actually a field of the opposite sign that cancels out the original field, and this process sort of cycles through. This is a turbulent approach. This is a classic approach using turbulence to do this and get these twists. There's a flux transport approach, which is a little bit different, which is just that it's not really turbulence, but it's some kind of magnetic instability. The structures just twist. It's very similar, and you get your poloidal field. There's a reconnection event, two reconnection events, one here and one across, that leads to these blobs that are ejected. Large-scale field is produced. And then there's a meridional circulation inside that sweeps the one sign towards the equator and one sign toward the pole. So you get your large-scale field merged towards the pole, which then again opposes the field of the original sign. So you can carry these vectors through, and this sort of toy picture kind of works. Now, the problem, so this is a more look at the alpha effect, which is the process of getting this poloidal field from the toroidal field. So there's a toroidal field. You have these helical twists one way or another that produce an electromotive force, and the result is a electromotive force that is aligned with the original magnetic field. And when you have dB by dt is curl of E, that gives you exponential growth when you get these kind of loops. So, and then the net result of these loops is a mean poloidal field, which you then continue this process, etc. Now, the common ingredients for all of the dynamos is an alpha effect, this poloidal twist. One way or another, you need to twist the poloidal field. There's the shear of the differential rotation. That's the omega effect. So this is, I should say, common ingredients of all large-scale dynamos as applied to the sun. And then there's some kind of diffusion or transport of a flux that carries the large-scale field from where it's produced to larger scales to the poles, for example. So these three effects, alpha, omega, and beta, are all needed in all dynamos. Now, and the other thing is that the dynamo is in the interior, but you need to get the field out to the surface. So there's a complexity in studying this problem, even numerically, particularly because the density range in the sun is so high. The convection zone at the base is, a tenth of a gram or so per cubic centimeters, and then all the way to the surface where the fields are observed, very, very low density corona. So that's actually a major difficulty in all this. But these basic ingredients are always present, and the detail. And what's a problem is that, so that is where the things actually occur in the sun is a bit of a problem. People don't agree on that. Nonetheless, the ordered field patterns show clear mean field behavior, which is amenable to analytic treatment ultimately one way or another. I mean, if you didn't see something ordered, it would be all chaos and it wouldn't be as interesting. If you see something ordered, then you know that there is likely some way to consistently explain it all. So just to see some of the complexity that confounds people, and then I'll step back from that and show that you can say some things that are true even despite this complexity. So the convection zone is here. Some people think that the entire dynamo goes on in the convection zone. Some people think that the alpha twist part of the dynamo goes on in the convection zone, but that the shear goes on in this shear layer beneath the convection zone, which isn't very turbulent. And so the rotation profile of the sun, why I say there's a shear layer, is that this is the observed rotation profile of the sun. Sun rotates faster at the equator than at the poles, and this is the convection zone slice. And at the very base of the convection zone is a strong shear layer where there's very little turbulence. So there's this, you have this combined fast rotation here, and increased rotation as you go outward here, decreased rotation as you go outward here, and a very strong shear layer with no turbulence in the region that just bounds between the radiative zone and the convective zone. But so there are these different types of dynamos that people argue about. Shear in the tachocline to get the omega effect, and that's part of the reason is that it's hard to store flux in the convective zone. So if you make strong flux in the shear layer, you can amplify it and then do a little bit of twist as you get up through the convection zone. And then there's the distributed version, then there's the flux transfer. So these are all debated, and I would say to some extent, for purposes here, more detailed questions about how and where the dynamo occurs. These consume careers to try to distinguish which of these, and people are studying this with various different ways. Now, to study the problem in different ways, you can use, there's all these different methods, observations, simulation, theory. A large effort has been going into kitchen sink kind of numerical simulations where you try to simulate the convection zone with as high a fidelity as possible. And they have limitations because of the dynamic range available to you. And so that causes a lot of problems. And for many years, the kitchen sink simulations weren't showing anything like what the 1955 theory of Parker with a cycle would show. No cycle period, no self-consistent alpha effect, etc. But nowadays, the simulations, the kitchen sink simulations, are showing more and more ingredients that look like the original mean field theories, which is sort of interesting. Then there's kind of minimalist simulations where you can take a piece of the puzzle and look at, not try to simulate the entire convection zone, but force, for example, the helicity and ask how it saturates, what the principles that dictate these kind of things. So so it's, when you look at this business, it's hard to sort, a little bit tricky at first to sort through, find the basic principles amidst all of the numerical simulations, and what limits the numerical simulations, and what's actually a physical result from the simulation, etc. Actually these details turn out not to be so important for what I want to say, because the theory change that I want to advocate applies in all cases. But just to give sort of a picture of what the kind of things people do with these simulations. So this is a simulation that's done. It solves the MHD equations, puts in a heat flux puts in heat flux at the inner boundary. This is actually observation. I was just going to show you that this. So it puts in a heat flux at the inner boundary, and allows allows convection to self-consistently generate. The and you, as a result of this, and you put in rotation and you put in convection, you get a net rotation profile that combines the result of rotation and convection that averaged over 100 years in their simulations, looks pretty much quite well to produce the solar rotation. And this has been a sort of even a recent development to get these rotation curves, to get convection to look like the solar rotation curve. And then there's the question, let alone getting the rotation curve, having it look like the actual, having it produce the field and such that you want. Now, so people run these codes, put in the magnetic field, and then measure out quantities that are associated with the mean field theory. And roughly speaking, the colors, never mind sort of magnitude, are starting to show consistency. That is to say, you can generate an alpha effect self-consistently by driving convection and putting in rotation. So convection and orbital rotation, the combination together without forcing any helical alpha effects, tends to produce an alpha effect. It also tends to produce cycle periods. These represent the flip and sign of the field, large-scale field, and the alpha effect, the sign of the twist, maintains constant value in each hemisphere during the cycle, which is also what you would kind of expect from the theory. Now, there are other examples of cycle periods. The problem with a lot of these simulations in interpreting them is the scales involved in simulations are tiny range compared to what actually goes on in the sun. So the sun has a viscous scale, a resistive scale, at these orders of magnitude, and a convection time scale down here. The simulation has this limitation that the resistive time scale, the viscous time scale, are very close to the convection time scale, and so you haven't really demonstrated clearly one hasn't demonstrated clearly in the simulations that any cycle periods are actually on turbulent turnover time scales. They're too close to the actual resistive dissipation time scales to know whether one is really getting the separation in the scales for the physics. But people view it as encouraging that the simulations are at least showing features in the past couple years that haven't been seen in simulations for the decades before. So, but keeping all that in mind, because the simulations are starting to show some convergence, better, in fact, convergence with the mean field theories, it's encouraging to continue with the mean field theory because they're simpler and they have predictive power and they get at the basic physics. And so in that respect, I want to consider not a simulation, but just a toy model that captures some of the key features of the dynamo and will get at the two ingredients that I want to include to augment the theory to try to reproduce this curve. Now, this luminosity curve. So this is the simple model. The interface dynamo is the case where you have a shear layer and you have an alpha layer that gives you your convective region at the base of the convection zone. This is a model that's the second most simplest. The first most simplest is what would be a distributed dynamo where the entire convection zone, the blur between the shear and the alpha layer are all sort of merged together in a single layer. This is the absolute simplest model that you can consider in a meridional slice to see the basic thing. So in the context of previous approaches to connecting the dynamo and X-ray activity, so it has been, of course, recognized that the X-ray activity, if the fields are produced inside the sun and then pop out and become buoyant, they have, of course, something to do with the dynamo theory. So is the X-ray activity and the rotation dependence have something to do with dynamo saturation in one way or another? What properties of the dynamo are relevant to explain that curve? So what's been done before typically is that one has some kind of a simple model, such as this putting together, as I sort of showed in a simple framework, and you write a set of equations for the components of the magnetic field, the toroidal field and the vector potential, which is a proxy for the poloidal magnetic field. modulo with these coefficients, the alpha coefficient, the beta coefficient, and there's the omega effect. And from these equations, you can construct what's called a dynamo number. It just gives you an indication of when, under which conditions, you actually get growth. And it's been argued that, and so this dynamo number is, for whatever reason, the quantity that people have focused on in trying to assess its dependence on rotation. The dynamo number that's been found, indeed, it does depend on rotation, but it has no saturation. And the dynamo number is only determining initial growth rate. It doesn't actually say anything about saturation of the actual dynamo, but it's sometimes attributed to, say, dynamo efficiency. So a large dynamo number is thought to mean a highly efficient dynamo. So if the dynamo efficiency somehow decreases, you might think that the strength of the dynamo is also decreased, or the saturation field also decreases.
Eric,
But
are these
yeah.
kinematic dynamo theories?
Yeah, so this is, and that's exactly the point. So this is all from kinematic dynamo, the connection between X-ray activity and dynamo that's been previously in the literature is always focusing on the kinematic theory. And so that's the problem, I think. And that's why there's been no good explanation from dynamo theory so far. ND, this isn't the most relevant quantity. You need to understand what happens in the nonlinear regime. Also, there's an important point, which is that which I'll describe in a moment, which has to do with this convection time and its relation to the correlation time of the turbulence. That has to be amended. And also, you need to make an explicit expression for the X-rays that connect the actual dynamo field produced to the X-ray luminosity. So these are the things that one needs to fix to get an actual connection between dynamo theory, even in the simplest model. And that's what I want to describe now. The first thing is the measured timescales in the Rossby number. The question over there was asked about. So the rotation period, it's commonly assumed, by the way, that the rotation period you can measure, and that's no problem, by time series photometry. And in fact, the good samples are using actual spot periods, not V sin I. So that's removed from those. But the TC, this convection time scale, is inferred from stellar models in the sense that the models for a given, so stellar models you can have a convection zone using mixing length theory, which gives scale height and turbulent velocity for a given color index. So you convert the stellar structure, produces a given color index, then you go back and you look at the scale height and the velocity of the convection zone to match that. So what you end up with is a convection time scale that's a function of a mixing length parameter, which is usually of order 1, which is the measure of the scale over which an eddy, a thermal eddy damps itself out, transports the heat, and then then it depends on the scale height and the velocity that come out of the stellar model. And then it's assumed that this convection time scale is the same turbulent time scale that enters into the equations for the dynamo, and that's a point that. So it's assumed that the convection time scale is also the eddy lifetime, or the turbulent correlation time scale. And this is important because in the coefficients for the dynamo, what happens is you imagine an eddy that rises up and twists, or in the alpha effect part of it. Well, it rises up and twists. It's under the action of the Coriolis force that makes it twist because of the conservation of angular momentum, so there's a Coriolis force. The time scale over which it lasts as an eddy twisting is the correlation time. So if that time scale is the convection time, then a natural time scale for that would be a convection time if under, you might normally think that. But so this is really, this mixing length is actually at the base, usually at the base. But that doesn't matter so much. Yeah, it's constrained by the luminosity. Yeah, exactly. But the point I was going to make here about this correlation time is that on the other hand, imagine that you have a system with very strong shear. So you imagine your eddy. So first, imagine the system just has that the convection time does determine the correlation time, which means that the rotation, say, is very slow. The eddy rises. The Coriolis time influences the twist, and then the natural mixing length just determines the correlation time of that eddy. But now imagine the case that there's a strong shear in the flow. And imagine that the shear time scale is much less than the model-determined convection time scale. Well, then the correlation time scale of that eddy is no longer the the convective time scale. It's the shear time scale, because the eddy will be shredded on exactly that time scale. And so you need to change. So this is very important, because then if you look at you have to define, so you can accommodate this by defining a new eddy turnover time scale that in the limit of large Rossby number, long rotation period goes as the convective time, but for small Rossby number goes as the shear time scale. I say shear time scale because you can imagine a rigid rotator that's rotating very fast as measured on the surface. It may not have, if there's no differential rotation, this argument is less. So I think there's a proxy. It's important that the surface measurements of rotation are actually a proxy for some kind of internal differential rotation in this characteristic. In the layer in which the alpha effect is produced. Yeah. So exactly. So the surface, what you measure and the surface rotation. So there's a kind of coefficient that if you knew what the surface rotation meant about the internal differential rotation, which is itself one of the challenges I would propose here, then that's the connection that you make. But so that's the first ingredient that I want, that you need, and you can incorporate in simple models, that hasn't been included in this, and that's the first ingredient: convective versus turnover time. And so there are two ingredients that I'm going to change the simple model to, which is going to be very helpful, as you'll see. The second ingredient is that I've shown these pictures of the dynamo, but in fact they're actually wrong. In fact, all the textbooks are arguably wrong in this respect, because these don't conserve magnetic helicity. And I apologize to those who've heard me say that before, but what happens is, if you look, so here's a loop which has no helicity, no twists. So helicity is a measure of linkage and twist of magnetic field lines, and their equivalence can be shown by taking a strip of paper, twisting it, tying the ends, cutting it, and then you'll find that you'll get two linked loops that have each a twist in them. But this is a conserved quantity in MHD, and effectively, by making a twist, I'm making a twist for free here. In fact, all of these twists have the same sign of the helicity. One is in the, so I've put these, but the point is that I basically made a link. These things represent, so if you see this picture and you imagine these loops that have been twisted, the mean poloidal loop here is now linked with the original toroidal loop. So I now have these two blue loops that are linked with the original toroidal loop, but I got those for free somehow. I don't have any links here, and I went from no links to links. So where is the missing helicity? The answer is that you should think of a field line as a ribbon. The ribbon is now, when you twist the ribbon, do the same motion, you get a small scale twist along the loop, which has the opposite sign as the helicity associated with the larger part of this loop. So when you look now at the picture, you have the overall toroidal loop, which is indeed linking these two poloidal loops, but if you calculate the helicity from the twist, it actually cancels out exactly the helicity from the other. Now, what that means is that you're building up, so the twist is not for free. That's building up small-scale magnetic field as the same time consequence that you're building up the large-scale magnetic field from the actual loop. And so there's a whole theory, and so you can rewrite the theory to include magnetic helicity conservation, that becomes a mechanism of saturation for simple dynamos. In other words, if I start with a system, I drive it with kinetic helicity, the system responds by growing a large, so I drive it with kinetic helicity, that's the alpha effect. I go my large scale field, but as a consequence of that, I'm building up the twist on the small scales. And when you correct the theory to include the magnetic helicity conservation, you find that the driver is actually the difference between the kinetic helicity and this small scale magnetic current helicity, the twist. So as you drive the system with the kinetic helicity, the small scale twist builds up and actually cancels out the growth, and it produces a mechanism for the thing to saturate. That's been now tested, and we did this in the theory. Simplest version of this is back here, and it's been tested with simulations where you actually force, not from convection, but you just force the helicity, watch the field grow, watch it saturate, and it agrees with the minimalist kind of dynamos. And so that principle leads to an analytic prediction as to how strong the field gets before it should actually saturate. So that is a saturation theory. The current state of the dynamo, so if you, those kitchen sink sort of simulations that I described, they don't have the theory for interpreting. So if you think of those as experiments, this is the best way to think of them. It's an ongoing effort to understand how they saturate. They do saturate. It's been an ongoing effort to understand and map the kind of mean field concepts into those simulations, and that's an evolving process. In the simpler simulations, where you have more control over what the forcing is and such, the saturation from helicity buildup it works, and it's become kind of an enterprise in other subfields as well to understand the tracking of magnetic helicity dynamics. There are folks here working on that, even in the MRI for accretion disk and such. So what I want to just so these two ingredients, the correlation time change to not match the convection time for fast rotators, and the saturation from helicity dynamics can be used to augment the theory. And by the way, a prediction of this helicity stuff is that in each hemisphere you should see twists and helicity of both signs. That's been an ambiguous thing that measuring the sign of the helicity has been an enterprise in the sun, and part of the confusion is because there are both signs present, and this is also something that's being sorted out. There is a recent evidence that, in fact, just recently, the magnetic field, the positive, negative magnetic helicity in the northern hemisphere, opposite to the helicity of the active regions. So the active regions are like the small-scale structures. The global sign is like the large-scale structure. So the dual sign of twists and such is something that's predicted that would happen as a consequence of all this helicity business, because you get both signs in both hemispheres, with the large scale in the southern hemisphere having the opposite sign as the large scale in the northern hemisphere, and the same reversal for the small scale fields. So that's and there's also an example of a kind of a structure that looks sort of bihelical. This is a writhe of one sign. The writhe has one sign, but then there's a twist along it with another sign. So that's the sort of, that is a whole nother, the details of the helicity is a whole nother talk in and of itself, but I want to point out that when you replace, so this was the toy model that I originally wrote down without these augmented changes, the two changes being, I've added now the the helicity theory to conserve magnetic helicity. So this is the kinetic helicity driving, and this is a magnetic helicity compensating thing. There's a time-dependent growth of this that comes as you grow the large-scale field that eventually quenches this. And there's and the eddy turnover time now is replaced. It's not a convection time, but it's this generalized eddy turnover time that itself depends on, that goes to the convection time in the limit of slow rotators and is the shear time scale in fast rotators. So these are and there's also an issue with there's also another thing, helicity fluxes, which enter in this case, which relate to the buoyancy, but that's also something that I can, so there's a buoyancy loss term in both the toroidal field and in the small scale helicity. The resistivity is actually Yeah, it can be included. It is included. You don't actually need it in the sense that so that's an interesting question. What's happened in the dynamo when you put the helicity conservation in? What happens is that if you allow the small scale helicity to build up, it actually shuts the whole thing down. And then only if you can get rid of the small scale helicity can you keep the field growing, essentially. But so to get rid of the small scale helicity, you could either have very high resistive dissipation, which is not possible in the astrophysical case. So instead, you have helicity fluxes. And so the fluxes act to alleviate the small scale helicity, and that's also why you see anything in the corona at all. I mean, there's buoyant flux of loss that go into the corona that in this picture takes both small scale and large scale twisted structures up in there. So the flux of the helicity into the corona is actually an integral part of the sustenance of the fast cycle period in this picture, because otherwise the helicity builds up catastrophically. Now now the thing is, you can then so what I'm going after now is to use the result of these ideas, putting it together to construct an X-ray luminosity and connect it to the field that's produced from the dynamo. So the first thing is that the saturated. So there's two sort of ways of thinking about how the field saturates when you solve this. One is that the poloidal field is the helical part of most of the helical part of the field is equivalent more or less to the poloidal field. The toroidal field is amplified by shear, which is not a helical amplification process, but the poloidal field has the twist helical part in it. So you can think of the poloidal field as saturating by matching the small scale helicity. So the helicity is conserved, large and small scales, then you can get an estimate for the large scale field strength associated with that. And that's the poloidal component of the field. And then the toroidal component of the field is further amplified by linear stretching on essentially a buoyant loss time. So this allows you to then, and so from the poloidal field, that connects with the velocity flow through its matching with this kinetic helicity. So you match this to this is the current helicity. It relates to the magnetic helicity, which is conserved on large and small scales, gives you an estimate of the large scale field, and then you can see that there's a connection with the velocity there. And yeah, it does. That's the point, though. So the idea is that it takes away some of the small scale, and so the helicity of the small scale is lost. Also some of the large scale, but it alleviates the buildup of the helicity to allow the dynamo to continue without its quenching. So let me let me just move on here. So this connects the magnetic field to this basically the thermal energy here, so the energy in the turbulence here, and modulo with this Rossby number. You can then combine this into an X-ray to bolometric luminosity simply by taking the magnetic field strength that saturates buoyant velocity, and times the characteristic radius at which all of this is produced, times a filling fraction that the flux penetrates through that surface. So this is a energy times a velocity times an area, and then times a angular filling fraction, which is that filling fraction of what the flux actually penetrates. When you combine this, out pops the convective luminosity, essentially, which is then basically the bolometric luminosity. And the result is this. So Lx over L bolometric, where bolometric has replaced this convective luminosity, it then has this dependence on the Rossby number as such. Now this lambda is simply a measure of, and it's a parameter, but it's a measure of, as you increase the luminosity of the star, extra luminosity of the star, how much filling fraction does the flux actually penetrate through the surface? That is not modeled in this, but the point is that if you allow that just to vary from 0 to 1/3, the range of Rossby number here, and so this is sort of a predictive check, a consistency check. It would be nice to know this number observationally. In other words, plot all the stars, measure the filling fraction of the flux of spots on their surface as a function of X-ray luminosity and stellar type. But this implies a narrow range of the dependence on Rossby number for this kind of fraction that fits in here. So if you put all this together, I've taken now the X-ray. This is from the paper where we do this. And this, just fitting this curve with the lambda equals 1/3 case, which is the one that works seemingly the best, it's not bad. So I matched this to just the measurements of the sun. I didn't actually fit the data in detail. I just had this go through the points for the sun, and then that's more or less the curve. So so what's happening is, of course, in the low rotation, in the low, large period, you're seeing the effect of the both the saturation of the magnetic field, its connection, and the fact that the correlation time is the convective turnover time. In this regime, you're seeing the fact that the correlation time is decoupled from the is just simply the rotation time. So it's the shear time scale. So basically you're independent of the Rossby number in this regime, because the eddy turnover time scale itself is proportional to the rotation time. Because, as I said, in that regime, if there's strong differential rotation would just shear eddies. So the correlation time is simply that which relates to the rotation time, given a proxy between the measured rotation time and internal differential rotation.
Did I understand correctly that this lambda is a parameter of the theory?
Yeah, the lambda.
Choosing it to get there.
Yeah, it's not even too bad if you pick a lambda that's this lambda is a parameter. It's a parameter, and the physical meaning is this filling fraction of the flux as a function of the X-ray luminosity. So there's a nonlinear dependence hidden in here of this actual Lx over L star, and that's the thing. The other parameter is this S, in the sense that this is a measure of the shear that the surface rotation is a proxy for. So in other words, you measure the surface rotation, but you don't know the internal differential rotation. So you have to, and you can ask what this has to be. The value I take for this is the value for the sun. So this one is fit for the sun. It turns out that this number is like 5, which is a measure of the.
Since this individual star is moving up and down.
Yeah.
Should this be fit to the peak for a given object, effectively?
Right. The problem is that you mean like see the sun, we have a peak, and right. So it's hard to. In a way, yes, maybe. It's just, but when you see these objects, you don't have, like most of these objects, you just get one shot at measuring them. So you're not following them in their, each object as their, or is that what you mean? Because each object you don't really have over a cycle period for the object, just measure that object in X-rays. Some of them you have time dependence and such, but others you don't. So the sun you do. And so, oh yes, so tau rotation is just the measured rotation profile from spots on the surface. Yeah, and then tau eddy is this is the correlation time of the eddy, but modulated by this physical ingredient that for fast rotators, the eddy turnover time just becomes the shear time scale, and yeah, in this picture, the eddy, the rotation time scale is the rotation time scale of the whole star, The eddy timescale is the timescale for a random component right, which would start out at something like some fraction of the convection zone scale height. It would start out at that size and then rapidly be shredded over some timescale, which is either the convective turnover timescale or the shear timescale, according to this formula. Time? Is it getting to the point? Okay. So that's basically what let's see. So let me just come back to this point here. Oh yeah, I did want to say. So okay, there's another interesting thing, which is that so after doing this, so another person, Christensen, did something differently, which turns out to be consistent, which is I thought was interesting. So he he looked at a bunch of simulations of dynamos, not just mostly planetary dynamos actually, and from simulations, and he plotted the saturation of the magnetic energy as over the rotational energy, and these are all in the low Rossby number regime. He took these to be in the low Rossby number regime. And he just took data from the simulations and found that they are saturated with the magnetic energy proportional to the rho v squared, basically. There should be another rho here. The point being that this is basically the convective energy in thermal convection determined in all of these simulations the saturated magnetic energy. It's a convective flux, yeah. Yeah, it should be. It should be really squared. Somehow the units should be right. This sort of thing. I don't know why that was a little bit of a. But the point. Yeah, it's actually averaged. It's some kind of an average that he defines. It's actually, and there's a little bit of trickiness in the average because there's a structural quantities that depend not on the energy content but on the various scales and such in the different simulations. There's some detail associated with the coefficient here, but the main point is that there's no dependence on the rotation. Like this just cancels out basically in this relation, and the point is that for these fast rotator simulations, the rotation has no influence on the saturated field strength, nor does the Ekman number or the magnetic Prandtl number. So the colors indicate magnetic Prandtl number, the ratio of the microphysical magnetic dissipation microphysical viscosity to the magnetic dissipation. Ekman number is the viscosity to the Coriolis force. There had been some thinking that the balance between the Coriolis force and the Lorentz force was a determiner for saturation, and that turns out not to be the case in these. This is consistent with the result that we also this other thing here. It's just consistent. The rotation independent for the low Rossby number regime. So that sort of just ends up being consistent. And then he actually used that to make predictions for field of a brown dwarf. If you use that scaling, you can predict where you might expect the field to be by using models and combining with it. In any case, this basic scaling is consistent. And if you think about it, it's not. I mean, what else? If the rotation drops out of the problem, what else can there be, right? Just the flux of and it's all going in the turbulence. So that makes sense. Fine. Yeah, the eddies are rotating. Right, but then they damp very quickly if they're sheared. So if there's strong shear, those eddies aren't going to last very long. And actually, the more Coriolis force you have, in principle, the better the alpha effect would be, except for the fact that the eddies are sheared more quickly as well. So the two effects kind of are compensating for each other. Finally, okay, so just last thing, and then I'll be done. In this stuff, I haven't included a dynamical equation for the orbital velocity. I have for the rotational velocity, but you can couple in an augmentation of this theory is to include the evolution of the rotational velocity as well. Then you can get the spin down prediction coupled into the dynamo as well, and that's sort of an interesting thing. There's very little work on dynamo theory where the rotation velocity is actually dynamically evolved as well, and they should all be coupled in. In fact, that has implications for fast rotators where you might produce fields and then produce explosions in other contexts as well. So anyway, just put these up here, and I think I should stop